Do you want it from the beginning, or uh, for the first class test, how much did we have? Was it just EK diagram, that means till before drift diffusion, or did we have drift diffusion? Hello? Hello? Are speak now, some of you, one or two of you, why don't you speak out? Fermi
No,
energy level was there.
Fermi energy level.
Ma'am, our CA1 syllabus was still concept of holes.
Yes, ma'am.
And then from the Fermi energy level, it was not the Fermi energy level. From the energy level, it was not there. It was still
Okay,
concept
fine.
of holes.
Okay. So concept of holes, that means even N0 P0 equation was not there, right?
No, ma'am. No, ma'am. No,
Okay,
ma'am.
so my question is, would you want to keep the syllabus from from the beginning, or would you like to start from Fermi energy? That means whatever we did in our first class test, we leave that out and we keep the portion after the first class test. What do you want to do? I have no problems. I'll be setting questions based on that.
ম্যাম ফার্স্ট থেকে হলে আমি জানি না বাকিরা কি করবে, বাট আমার মনে হয় যে ফার্স্ট থেকে হলে একবার আমাদের ওটা রিভিশনও হয়ে যাবে।
Revision হয়ে যায় না, দেখো আমি বলি, there are two aspects of it. Those who had seriously studied for the first class test already have that portion studied. Those who did not study that properly has it undone. So if I keep that for the first class test, it is advantageous to both, in the sense that those who did not study it will now forcibly study it for the second class test and get prepared for it, and those who had studied we'll just have a brief recap of it. So if you're studying it twice, then I think before your final exam, just a glimpse will help you through that part. That is one advantage. And the second, the disadvantage is the syllabus becomes huge. So if you think that you will not be able to manage it, then it's better to keep the second portion. But if you think you'll be able to manage it, then it's wise to keep the first part also. Now, if the range is large, if it is full syllabus, then the depth of questions becomes shallow. That means the questions are easier because I get a wide span from which I can formulate the questions. Therefore, I can put up with simple questions. But the minute your syllabus gets shrunk, so I have to formulate questions from that little part of the syllabus. I just can't help out including tougher questions, because I have to make questions, because how many simple questions can I make from them? So that is there. So it all depends on what, okay, you give a thought about it, you discussed amongst yourself. I always ask you to take your opinion. I don't give it up to you as dictating like, no, this will be the syllabus, because after all, it is you people who have to study. After all, you have to study the whole syllabus. So what will be manageable for you, you let me know then tomorrow, then I could proceed with it. And this time I don't think it is full MCQ. Have you been informed about that as well? Because a little bit writing will also be there, I think.
Yes, ma'am. It was informed to
Okay.
us.
What, subjective and objective, right?
Yes, ma'am.
And total marks, how much?
Ma'am, not exactly, but sir has told us that it will be around 25 to 30.
25 to 30. Okay. So If it's written questions, MCQs, let's see what will be the pattern of the question. So if it's 25 marks question and if it's not MCQ, then if you want to exclude the first part, it can be done. If you want to keep it, it can be done. I will not give you questions, I think, more than 5 marks. I will give you, even if it's written questions, I will give you questions for 5 marks. I'll be giving you more model questions. So that never becomes a problem. So that will be done. So you write, you don't write pages and pages. Maybe I give you like, with the help of Fermi Dirac distribution function, uh, discuss Fermi energy level for 5 marks. So you have enough to write for it. Okay. So that would be the pattern of questions, that the way it would go. So you tell me, let me know tomorrow. If you can't decide, then I will take a decision. But if you can let me know and the class agrees unanimously that full syllabus or only second class test syllabus, or only after the first class test, whatever you have done. So you let me know, we'll decide tomorrow. Okay. So that's something important. It needs to be informed tomorrow because I need a week's time to prepare questions and upload and then send you links and things like that. Okay. So that would be done. Now, okay, Devapriya, share the screen. Fine, you've already done it. So this is a familiar diagram that you know, and this shows you the built-in barrier potential. I would be pulling up a bit fast. I want to end this equation part today. So Vn is equal to Vt ln NaNd by Ni square. This is already that we have done earlier, and EVBI is the barrier potential. EVBI is the barrier potential. What does it mean? So electrons moving from N to P region will have to surmount this energy barrier in moving from N to P region. Okay. Acha, next page share karo Devapriyo. I would be going equation wise, ekdam, one after the other. Equation 8.1. Next page. Yes, fine. So what they have done is a little bit manipulation of the previous expression. So in that previous expression, they have divided by Vt, that is Kt by E, and they have taken exponential of both the sides and again reciprocal. You just work it out yourself. It's very simple. So we land up with this equation. I'm not going into the mathematical derivations. One or two lines you can manage on your own. I'm just giving you significance of what we are doing. So we land up with this equation, that is equation 7.1, that is Ni square by NaNd exponential minus EVBI by Kt. Now, if there is complete ionization, then we can write Nd, that is donor ion concentration at equilibrium, is Nn0, as we had discussed yesterday. N is number of electrons or electron concentration, that is number of electrons per unit volume. Small n suffix is the N region, 0 is equilibrium. So Nn0 is the electron concentration in the N region, that is majority carrier electron concentration in the N region at equilibrium. Majority carrier electron concentration in the N region at equilibrium. Okay, that is Nn0 and that is equal to Nd. Okay, now you know that from law of mass action, as we had discussed earlier, you get the next equation, that is Np0. What is Np0? We had discussed yesterday also in that table. Np0 was equal to what is Np0? It is minority carrier electron concentration in the P region at equilibrium. Okay, that is Np0, and that is equal to Ni square by Na. Okay, that is equal to Ni square by Na. Okay, so that is what is written over here. So if you make a small substitution, of equations 7.2 and 7.3 into 7.1, that is these two equations, the one ticked ones, you substitute in equation 1. Okay, and then if you just put values, substitute values of Na as Ni from here, and Nd from here. Fine. If you do that, if you do Na from here, substitute Na from here and Nd from here, then we have an equation, and that if you simplify, you get This equation 7.4. This equation, I'm double ticking this equation 7.4. So what does it say? What does it shows you? What is on the left hand side? Everything what I'm saying is written in these text. Okay, if you go through it, you will understand. So what is NP0? What is NP0? NP0. That means minority carrier electron concentration in the p region at equilibrium is given in terms of NN0 exponential minus EBBI by KT. What is NN0? It is majority carrier electron concentration in the N region at equilibrium. So it is basically, look, on the left hand side, it is, so what is the concept? What is the concept? Look, we had the PN junction. We had the, I'm going a bit fast. If you need my speed to be decreased, please tell me. Okay, please tell me. So what happens? Electrons move, I'm writing E minus, electrons move from the N to the P region. Okay, so when electrons are moving from N to the P region, they are doing it by surmounting an energy barrier of EVBI, right? EVBI, that is, they are surmounting the energy barrier of EVBI. That is the numerator in the exponential term. KT is as it is. Now, what is NN0? NN0 is the this is NN0. NN0 is here. NN0 is electron concentration, majority carrier electron concentration in the N region at equilibrium. And what is NP0? NP0 is the minority carrier electron concentration in the P region at equilibrium. So what does this equation show you? What does this equation show you? What does this equation show you? It gives you the relation between this NP0 and this NN0. That means the relation between the majority carrier electrons in the N region and the minority carrier electrons in the P region at equilibrium. Okay, so it gives you the relation between the majority carrier electrons in the N region, that is NN0, and minority carrier electrons in the P region, that is NP0. And why that relation is important, because a little bit later we will see that this is an equilibrium. This is an equilibrium means in an unbiased situation when no electrons are moving from N to the P region. The minute we will see that the minute we apply a forward bias, what is going to happen? Electrons are going to move from N to P region and this equilibrium will be disrupted. And then what is the relation between this majority carrier electrons in the N region and minority carrier electrons in the P region? Why it is important is because when electrons are moving from N to P region, they are becoming minority. Electrons were majority carriers in the N region, but the moment they move into the P region, they get the status of minority carriers. So as soon as you apply a forward bias that we're going to see just a few minutes later, that this equilibrium situation is disrupted, and there we will again show you a relation between NP, that 0 won't be there, NP and PN. Okay, so we are actually looking to see that in the forward bias situation, how the equilibrium would be disturbed and what would be the relation between the majority carrier electrons in the N side and minority carrier electrons in the P side, because electrons moving from N to P has the status of minority carriers in the P side. Am I clear? Am I clear, students? I'm going fast. I could still increase my speed if you want. If you want, I could decrease my speed. বলো, ফিডব্যাক দাও। আমি কিন্তু একটু স্পিড বাড়িয়েই আজকে স্টার্ট করেছি। বলো feedback.
Okay.
Okay, yes, okay, okay,
Yes, ma'am. Yes, ma'am.
ঠিক আছে, চলো, ফাইন।
Yes, ma'am, ঠিক
Okay,
আছে।
I would be, ঠিক আছে, have speed ঠিক আছে তো? একটু
হ্যাঁ
স্পিড আপ
ম্যাম ঠিক
করলাম।
আছে।
হ্যাঁ, এবার একটু স্পিড আপ করব, because I think we have a long way taking classes and you have got adjusted to my frequency. So now it will be a little bit speed up. If you have problems, please let me know. If you have problems understanding, let me know. I would again slow down. Because I have long way to go through the syllabus and I need to just increase my speed a bit. Okay, so this relation is something that we have learned, that is NP0 is equal to NN0 exponential minus EVBI by KT. Chalo, the prior diagram, the figure below this, all what I have said is written in the paragraphs, and all known things are written in these paragraphs. Just go through it. If you don't understand anything, you ask me later. So now you see that we have applied a forward bias, and VA is the amount of forward bias potential that is applied. Okay, so this is E applied, this is E applied, and this is E, that means the direction of the electric field. They are in opposite direction, as we have discussed many a times earlier. Okay, so this is WP, that means width of the neutral. W stands for width of the neutral P region, or the bulk semiconductor P, as we discussed yesterday and day before. And Wn is the width of the N region, is the bulk semiconductor in the N region. Fine. And you see that as we have discussed earlier, so if VA is the amount of forward bias voltage applied, that means positive to the P side and negative to the N side, and amount VA has been applied, then you see that the equilibrium condition is disrupted, and the barrier potential has been decreased by an amount of the applied forward bias. And now the barrier potential in the unbiased situation was EVBI, and now it is EVBI minus VA. So you see that the barrier height here also, you can see that the barrier height is decreased by the amount of the applied barrier, by the applied potential, the forward bias potential. Yes. Go to equation 8.5. Okay, now if we just, now we had the previous equation, that was the relation between NP0 and NN0. What was it? It was NP0 was NN0 exponential EVBI by KT. Okay, so that was there. Now what I said is, the moment you have applied a forward bias by the amount VA, okay, the equilibrium situation is disrupted, and then since the equilibrium is disrupted, you can no longer write the terms as NP0. So what you write is NP. What is NP? That is the minority carrier electron concentration in the P region, not at equilibrium. That means after the application. What do you mean by equilibrium? Now in equilibrium, when there was no bias applied in the neutral P region, there was a definite number, depending upon the doping concentration, there was a definite number of holes per unit volume or hole concentration. There was a definite number of electrons per unit volume or electron concentration, or the minority carrier concentration. Okay, and the previous equation of NP0 is equal to NN0 exponential minus EVBI by KT. The equation just we discussed before this, that is in equilibrium situation, was relating the number of the minority carrier electrons in the P side with the number of majority carrier electrons in the N side at equilibrium when no biasing was applied. The moment you applied a biasing, that is when the moment you apply VA, what happens is electrons move from N to P side. So now in the neutral P region, the number of electrons has increased because electrons have moved from N to P region. So the electron concentration there is not NP0 now. Okay, it is NP, because it is not the equilibrium condition, so that 0 has been removed. Okay, so that NP is over here, and what by how much will it be different from the equilibrium condition is, the equation remains as it is. The equation remains as it is. And I'm taking a class, right? Call me after 9:15. Okay. Okay, so NN0 is exponential minus EVB. So sorry, what will be the amount of the change in that NP? What will be the amount of that change in NP? That is whatever equation we had earlier, that is NP0 exponential minus EVBI by KT. Now VBI in the exponential term will be replaced by VBI minus VA. It will be replaced by VBI minus VA, right? Okay, so that is the only difference that we have. So if you break it up into parts, it is NN0 exponential EVBI by KT, and the next part, that is exponential EVBA by KT. Now what is this first part? This first part, NN0 exponential minus EVBI by KT. This part, what is this part? This is nothing but NP0, because that is the equation that we had. NP0 was equal to NN0 exponential minus EVBI by KT. So in the next equation, you replace this by NP0 and exponential EVBI by KT remains as it is. So therefore, your final expression is NP, that means the minority carrier concentration electrons in the p region in the forward bias situation or in the non-equilibrium situation is NP0. That means whatever electron concentration was there in the p region at equilibrium, exponential EVBI by KT. Okay, so this is basically relation between NP and NP0. That means the minority carrier concentration in the p region. Okay, the minority carrier concentration in the p region. That means both sides of the equation are now showing the minority electron carrier concentration. Left hand side without the zero is when forward bias is applied, that is in non-equilibrium situation, and NP0 is in equilibrium situation. Okay, with the exponential part. Okay, is it clear? Is it clear? The previous equation, that is NP0 equal to NN0, was relating minority carriers on the n side electrons and majority carriers on the p side. Okay, but this relation is relating to both minority carriers in the n side in non-equilibrium situation and in equilibrium situation. Okay, this relation is important. This relation is important. Okay, is it clear? Go to the next equation, equation 8.7. This is for electrons. Similarly, similarly you have for holes. Fine, fine. Similarly, you have for holes. Similarly, you can find out the equilibrium concentration of the holes in relation to the non-equilibrium condition of holes. So that gives you this equation. That gives you equation. Similarly, Pn is equal to Pn0 exponential EVBA by KT. What is Pn? Pn is the minority carrier hole concentration in the N region in non-equilibrium, and Pn0 is the hole concentration in the N region at equilibrium. Both minority, that means both in the both in the N region. Minority carrier hole concentration in the N region in non-equilibrium condition, that is the left hand side, and Pn0 is minority carrier hole concentration in the N region at equilibrium. So this equation is relating to N region. The upper equation that we saw was relating to the P region. Clear, students? Is it clear? Is it clear? Yes, I'm just rushing through. Okay, okay, fine. Next, you move to equation. Okay, let me give you an idea of figure 8.4. Yes, let's discuss this figure. Let's discuss this figure. Okay, now this is what we were discussing right now. The equations, look, this is the depletion region, this is the depletion region, this is the metallurgical junction x equal to 0, sorry, this is the metallurgical junction x equal to 0, x equal to 0 over here. Okay, this is x equal to xn, x equal to minus xp. So right at here they are giving what is Pn at Xn. That is what I said, that this is Pn would be minority carrier hole concentration in the N region at equilibrium. And why they are giving you Xn is because just at the starting of the neutral N region at location Xn is what we have derived right now. It's Pn0 exponential EVA by KT. Similarly here it is NP at minus XP. At this location, NP at minus XP is equal to NP0 exponential EVA by KT. Okay, so this is hole injection because hole is moving from P to N, and this is electron injection because electrons are moving from N to P under the application of the forward bias VA. Clear? Is it clear?
Yes, ma'am.
Fine, and these are levels of the equilibrium concentration, NP0 and PN0. Okay, NP0 and PN0. Fine. So now let's go to equation I would be excluding equation 7.8. We straight away start from equation 7.9, or in this case it's 8.9. Yes, lots of marks to be removed. Yes, yes, stop. Fine, fine, fine. Let me remove these marks just a minute. So now we are into looking into something called, I would do the derivation for the continuity equation tomorrow or maybe later. Let us not now assume, let us now assume what it is. And then I would derive the equation for you. It's 4 or 5 lines of derivation. It would take around 15-20 minutes. So today I don't break continuity of teaching. So this is something called the continuity equation. Now, this is something called the continuity equation. This is the continuity equations for Pn. What is Pn? It is whole concentration in the N region, that is minority whole concentration in the N region. Okay, and similarly, this is the same for the NP in the P region. This is for the P region, that means it is for NPs, minority carrier electrons in the P region, and this is for the N region, that is minority carrier holes in the N region. Okay, so now what we have is we have already discussed in our drift diffusion chapter that there are drift current densities and there are also diffusion current densities. Okay, so when you are placing them in very small or not small, when you're placing them in electric fields, then what is going to happen? Both drift current as well as diffusion current, both are going to flow. Diffusion current is going to flow even because even when there is no field applied, and drift current will flow when you have applied an electric field. So now what does continuity equation mean is, it is a phenomenon of which I'll be discussing that more in details when I discuss continuity equation to you. But right now there is one big chapter on it called ambipolar transport. I'm not going into it, but it means is the concept is that I said just now is, and even the previous equations defined is, whenever you're applying a forward bias and electrons are moving from N to P region, electrons are having the status of excess minority carriers in the P region, right? Because there was a certain minority carrier electrons in the P region. When electrons are moving from N to P region, the difference amount of electrons from the equilibrium situation is nothing but excess minority carriers in the P region, excess minority carrier electrons in the P region. Similarly, you'll have for holes, whenever holes are moving from P to the N region, the excess amount from the equilibrium condition would be treated as excess minority carrier holes in the N region. So this continuity equation relates basically is an equation involving these excess minority carriers, electrons in the P region and holes in the N region. And for the two regions, we have two different equations. Okay, and right now you take this equation, assume this equation to be there, and later I will go in for the derivation, and then it will become crystal clear to you. Now if you assume this equation 8.9, it shows what? Double derivative with respect to x. That means you are trying to find out what is delta Pn. Now in this situation, let me explain the terms. What is delta Pn? Delta Pn is nothing but, it's written I think a little bit in the upper paragraph. Delta Pn, just after equation 7.9, it is nothing but Pn minus Pn0. This delta Pn, yes, if you just bring it down a bit. আরেকটু নামাও দেবপ্রিয়, আরেকটু উপরে আছে ওটা। Yes, fine, wait, just wait. Yeah. So this delta Pn is nothing but Pn minus Pn0. That means it is excess minority carriers, holes in the N region at non-equilibrium, minus equilibrium. Pn is the equilibrium concentration, Pn0 is the, sorry, Pn is the non-equilibrium condition when you apply forward bias, and Pn0 is the equilibrium condition. So delta Pn is the difference between the two amounts and gives you excess minority carrier hole concentration in the N region. Fine, in the N region. Yes, now you go to equations 8.9. Okay, fine. This equation, let me just erase these marks. Okay, now if you look into this equation, both these equations, so you are taking double derivative, of delta Pn. You know what delta Pn is? It is Pn minus Pn0 with respect to x. What is x? X is nothing but your x coordinate. That means this is xn, this is minus xp. So x is the stretch of length. From the x is equal to 0. It is the stretch of length along the P and the N regions. Okay, stretch of region. Now, what is LP? I'll come to the derivation, it will become clear. LP is the diffusion length. Okay, and it is given by uh, dp tau p0. dp is the diffusivity of holes, and tau p is the diffusion time. Means what? We have discussed this phenomena. Like, instead of going into the derivation, I'll do the derivation, I promise you. Let me go into the physical significance of this. That means, what is tau p0? This is this tau p0. What is this tau p0? Now remember, I told you, when the holes will diffuse from, what we are discussing, this Pn0, that means we are talking about the excess hole concentration in the N region. So we are basically concentrating in the N region. So what happens when you apply a forward bias? Holes are going to move from P to N region. Therefore, there will be this term delta Pn. There will be this term delta Pn, which is Pn minus Pn0, which is Pn minus Pn0. That means initially, before holes moved from P to N, it was Pn0. When holes have moved from P to N, it is Pn. So this excess amount is Pn minus Pn0 is delta Pn. So you are taking the derivative of that delta Pn with respect to your distance x. Okay, and what is LP? It is the diffusion length of holes. It is the diffusion length of holes in the N region. That means what I told you earlier also. If you think in terms of electrons, it becomes easier, that when electrons are moving from N to P region, what happens? They move for a certain time in the P region before they recombine with a hole. They drop into a hole. Okay, they recombine with a hole and a bond is made, and it is the relative motion of holes which pushes the holes from P to N. So what is tau P0? Tau P0, this term over here relates the distance for which the hole travels in the N region before recombining with an electron. That means it is tau P0. That means it is the diffusion time for holes in the N region. That means you treat them as entities, holes and electrons, still before they recombine. So if tau N0 or tau P0 gives you the time for which the electrons, P for holes, N for electrons, the time for which they move in the neutral P and N regions before recombination. So with respect to that, what is the length for which, what is LP? LP is nothing but the diffusion length of holes in the N region. That means how long, if this is the neutral N region, then what is the length in the N region that the hole moves before combining with an electron and making a bond. So that is LP. So this relation, continuity equation, I am removing all the marks. This equation, continuity equation, gives you this change of excess minority carrier with respect to x and with relation to the diffusion length. This is in the N region, and similarly in the p region it will be for electrons. So that is the continuity equation. That is very important because it gives you the excess minority carrier concentration in the n and the p region in non-equilibrium condition, with the concept that whenever electrons move from n to p, they become minority carriers in the p region. Whenever holes move from p to n, they become minority carriers in the n region. So these two are the two continuity equations of electrons and holes. Okay, I think for this much, if you and n region is for x greater than xn, and p region would be definite for x less than minus xp. Okay, so this x less than xp. So this is the modulus it is given, minus sign is not given. Okay, so these are the two continuity equations. You understand, just understand whatever I have told you. When we go in for the derivation, you will understand how these equations have come about. It's not difficult, maybe 4-5 lines of derivation and few concepts. That will be done maybe tomorrow if we get time. So is it clear, students? These are the two continuity equations. Is it clear?
मैम
Is it clear?
मैम डीपी का की बोलें
কোনটা?
मैम डीपी
DP আর DN মনে আছে? ডিফিউশন চ্যাপ্টারে ডিফিউজিভিটি অফ হোলস আর ডিফিউজিভিটি অফ ইলেকট্রনস বার করেছিলাম, ডিফিউশন কোএফিশিয়েন্ট। ফাইন, ইট ইজ আবার ওয়েবেক্স সিগন্যাল দিয়ে দিল 5 মিনিট, আজকে শেষ হবে না, কালকেই শেষ করব। তো ডিফিউজিভিটি অফ ইলেকট্রনস এন্ড ডিফিউজিভিটি অফ হোলস, দ্যাট ইজ DN এন্ড DP। ডিফিউশন চ্যাপ্টারে যেটা করিয়েছিলাম মনে আছে তো, একটা প্রপোর্শনালিটি কনস্ট্যান্ট এসেছিল, দ্যাট ওয়াজ কল্ড DP ফর holes and DN for electrons, that diffusion coefficient. Okay, so move on to the next equation 8.11. আজকে ভেবেছিলাম শেষ হবে, হবে না, কালকেই শেষ করে কন্টিনিউটি ইকুয়েশনটা সময় থাকলে বলে দেবো, কোয়েশ্চেন্সও দিতে হবে। দরকার হলে কন্টিনিউটি ইকুয়েশনটা বাদ রাখবো, এই ইকুয়েশনটা ধরে ইউ proceed with the question answers. Next week we'll go in for the continuity equation. Okay, fine. Next page. Next page. Shall I continue or shall I stop? Shall I continue or shall I stop? কি বলছো? মাথায় ঢুকছে? আমার অসুবিধা নেই কিন্তু। Shall I continue with the equations or shall I stop? 3-4 minutes আছে। ঠিক আছে, আর দুটো কটা ইকুয়েশন পড়িয়ে দিই। Okay. Now what we have to do is basically that we have got the two continuity equations with respect to holes and electrons. Okay, now we have to set in a few, we will go in for the solution, though those are differential equations that you have seen, and it is differential equation of a known form for which the solution is also defined. We'll see it in later in a few two equations later. So the solution for these two equations, differential equations, is also the form of the solution is defined, from which we need to find out the constants or coefficients from the boundary conditions. Okay, so for that we need to set in order to solve for these differential equations, we need to set the boundary conditions. Now I would stop after defining the boundary conditions and the final form of the solution. Tomorrow we would continue. So look, these are the four equations, the two equations that we already know. The two equations, that is Pn xn, যেটা আমরা আগেই define করেছি, is Pn0 exponential minus EVBA by kT. We discussed just few minutes back. Np, that means this is minority carrier holes in the n region in non-equilibrium condition, and this is with respect to equilibrium condition. Va is the barrier height or barrier potential. Okay, in forward bias condition. So similarly, this is the equation. Now if you look into this equation, what does these two boundary condition, what does this mean? What does this mean? The first one, Pn for x tending to infinity is Pn0. Pn for x tends to infinity is Pn0. That means I need to draw the junction. Okay, this is your minus xp, this is your xn, This is the W x equal to 0. This is x equal to 0. This is neutral N. This is neutral P. This is the depletion region. Fine. Okay. Now, Pn. What is Pn? When holes will move from P to N region, when holes move from P to N region, the excess hole concentration in the N region is Pn. Okay. So, this is at x equal to xn, you say it is Pn. That is why they have written Pnxn over here. That is why they have written Pnxn over here. Now what will happen? These holes will move for a distance Lp, as we have discussed, Lp, and then they are going to recombine with the hole. So at very large distance from the junction, that x tends to infinity, all the holes which have moved to the N region has actually recombined. So at very large distance from the junction, the hole concentration or the minority carrier concentration will be almost equal to Pn0, that is the equilibrium concentration, because the excess carrier holes which have diffused